Guys, Hi guys. In this lecture, we're going to talk about boundary conditions. And in particular, we're going to talk about a specific way that the electric field and the potential changes at the boundary of a surface charge. So that could be a charged sheet, any side of charged shell, could be a cylinder, it could be anything you want, but the electric field and the potential are going to change in a very specific way. Okay, let's get started by thinking about the electric field close to a charged sheet, okay? And when I draw this picture, obviously I'm drawing a flat charged sheet, but I want you guys to consider that if you get close enough to any charged sheet, it will look flat, okay? But this is a sheet from the side, so that's important to remember too. Okay. So think about that. And let me remind you guys, this is a sheet from the side. Okay, if it's a positively charged sheet, then I know that the electric field is going to point away from it. Okay, and if you remember, if this is an infinite sheet, the electric field is actually constant. Okay, no matter how far away I am from the sheet. Which is kind of funky, and rightfully so, because there really isn't any sort of thing that is an infinitely large charged sheet in real life. But if you're really close to even a non-infinite sheet, okay, it'll act like an infinite sheet. All right. So the electric field is pointing in the direction that a positive charge would move, which is away from this positively charged sheet. Okay, if I were to draw a little coordinate system here, and I'm going to define x being the direction of the electric field, at least on this side of the sheet, y is perpendicular to that. I can also draw a graph that describes how the electric field is changing with x position. So this is the electric field in the x direction. Of course, the electric field in the other directions are just zero. Okay, remember some potential units for electric field. You can use newtons over coulomb. Let's call this meters. Put some arrows here. Okay, so the electric field here, the way I've defined my coordinate system, it's positive and constant on one side of the sheet and negative and constant on the other. Okay, so this is what it looks like for a charged sheet. And again, any sheet that I get close enough to will look like a charged sheet. Okay, I want you to notice that this here is a discontinuity. This is what we would call a discontinuous function. And I did link to a Khan Academy video if we just want to recall what the difference between a continuous and a discontinuous function is. Okay, if I were to calculate the difference between the electric field in the perpendicular direction above this sheet and the electric field in the perpendicular direction below the sheet, I would get 1 over epsilon times sigma. Okay, part of that, if you guys remember, the electric field for a infinitely charged sheet, and some of these ones are good to remember, or at least have written down somewhere handy, is that. So I could get this directly out of the equation here. I'm going to make this actually a n hat. Okay, oops, that's too big. Where n hat points away from the sheet. To the sheet. Okay, so I could get this out of the straight math. The book uses Gauss's law to get this. Okay, but I want to make it clear when I I'm thinking about different sheets, particularly things that are not infinite sheets, I can still do this, but it's important to remember that we are talking about just above, okay, and just below, okay? So not talking about way above here and then way, although it would work for this particular sheet, but if I'm thinking about a different charge distribution, this is true, okay, for all charge distributions or all sheets, but I'm thinking about just above and just below, okay? So this is the importance of these boundary values of a sheet, okay? True for any charged sheet, okay? So any charged sheet is going to have this discontinuous electric field at the boundary, and this is going to describe the scale of the discontinuity, okay? So the bigger jump is going to indicate a bigger charge density. If it's a smaller jump here in the electric field, it's a smaller charge density. If there is no charge density, that's zero. Obviously, that's going to be zero, okay? If we look at what the potential looks like for this particular sheet, I can draw that as well. Different color. All right, let's draw some axes. Now we're going to do the potential. And units of potential, we could use volts. Let's just use volts, okay? And in this case, the potential is going to look like this, okay? Something like that. And here we've shifted, so we are, if you guys remember from the reading or from the lectures, when you're thinking about infinitely charged sheets, it actually gets a little funky when you say the potential is zero at infinity, so you have to define it to be zero somewhere else. So here I'm assuming that potential is zero at the sheet, because we can put it anywhere we want. Okay, it's just going to shift things. All right, so I like this because, right, you get an agreement when I take the negative of the gradient of this line here in these different quadrants, I calculate the electric field. Obviously, the slope here is constant. Here, the slope is negative. When I apply that negative sign, I'm going to get a positive slope here. It's in that weird quadrant where we don't really think about taking the slope very often. But I'm going to end up getting a positive value for the gradient. Okay, and then when I apply the negative sign, I get a negative electric field. Okay, but what I want you guys to notice about this particular function is that the potential, kind of running out of time here, or out of space, the potential is continuous, okay? And in fact, the potential is continuous at any boundary, okay? At any boundary. Cool. All right, so we got discontinuous electric field and a continuous potential. All right, so let's summarize that a little bit. Okay, we're going to do some in general things here. We're going to generalize. Okay, the perpendicular component of an electric field has a discontinuity at a surface charge boundary. Okay, and this is only for a surface charge. Okay, so for example, if I had a uniform charged sphere, okay, the electric field would look something like this, where this is the surface of a uniform charged sphere. Okay, this line actually isn't discontinuous because if I approach this point from either side, both of these functions are approaching the same value. Okay, so this is an example where it is not discontinuous because there is a volume charge. There's charge throughout the volume, not just on the surface. Okay? All right. In general, the parallel component, so this is parallel to the surface of E, is continuous. And if you're thinking about a conductor, it's actually 0. Okay? And the voltage or the potential is always continuous. So these are also ways that you can check your solutions to make sure they make sense within these rules. Okay, and you can also, of course, you should be able to eyeball a potential curve and see if it corresponds to the right electric field curve. All right, let's just do a little example. Again, there's more in the reading, so I do suggest you guys do the reading, but I don't want to just copy and paste the reading here in this particular lecture. But the reading talks about how you can use Gauss's law and line integrals to kind of come at the same relationships. Oh, actually, I do want to go over. Let's look into this one here with a bit more detail. I'm going to draw a charged sheet. Let's see if I can do this very well. Okay, and I'm going to actually do a line integral from above, just like the book does, to below this charged sheet. So from B to A here, and this is going to be my DL. And I'm going to use that to calculate the potential above and below the sheet. So the potential above minus the potential below this particular sheet will be equal to, that's how we define the potential, this line integral from B to A of the electric field dotted with our path. Okay, if my DL, this line, gets really small or goes to 0, okay, then I know that this part of the integral, this part has to go to 0 because this thing's going to 0. So the whole darn thing is going to go to 0, okay. And what that tells you is that, right, the V above minus V below is equal to 0, and therefore V above has to be equal to V below. Okay, so that's how we know that it has to be continuous. If I approach, just like I said here, if I approach, or I can go here, I approach the potential at a particular point from two sides of my sheet, I'm getting the same answer. Here, if I approach it from two sides of the sheet, I'm not getting the same answer. That's the difference between continuous and discontinuous. Okay, so I'm going to use this here to derive another useful relationship. Okay, I'm going to take the gradient of the right-hand side. And I'm going to do this on the next page. Let's see. Oh, sorry. So I've got this relationship where I know that the electric field above minus the electric field below for this sheet is going to be equal to 1 over epsilon naught times the charge density. And now this is a vector. I know it's going to be normal to the direction of my sheet, okay? I can use this in combination with the fact that I also know, right? We know that the electric field is given by the negative of the gradient of our potential. So I can write instead of writing the electric field, I can write this in terms of the gradient of the potential. And I'm going to have to throw a negative sign in there somewhere. I'm going to put it on the right-hand side. Okay. I'm going to, if I write a special version of our gradient here, where I'm just considering the rate of change of something in the normal direction. Okay, so this is going to be my new grad, where I'm just thinking about rate of change. Okay, just rate of change in the normal direction. So that's perpendicular to the surface. Okay, then I can just kind of take the guts out of this. Basically, I'm going to get rid of the vector bit, and I'm just going to take the guts. Okay, so the guts of that are going to be that if I take the rate of change of the potential above the sheet, and I'm taking that, subtracting the partial derivative with respect to this normal direction of the rate of change below the sheet. How quickly does it change above? How quickly does it change below? That's got to be equal to -1 over epsilon naught times the charge density. Okay, so same deal here. If I go back to this bad boy, the rate of change, if I were to calculate the slope here and the slope here, okay, that would be another way to derive this particular discontinuity. All right, because in this case, the normal direction, it's going to have different directions on either sides of the sheet, but it's aligned with the x direction. It's parallel or anti-parallel to it. All right, so that's another useful relationship that's showing how what's happening at the boundary of these surface charge distributions can tell us something about the electric field and the potential. Okay, let's just do one more example. Let's apply this to a sphere, just to show what that looks like. Okay, so I'm going to draw here. This is a sphere. It's got a radius r. Okay, and this is going to be a shell. It's a shell with a total charge q. Okay, so I'm not giving you the charge density. I'm just giving you the total charge. All right, let's calculate what the potential is the old-fashioned way. So the potential on the outside of this sphere, if I pick a point here and call it R, I've got to calculate a potential that goes all the way from infinity, this is my start point, all the way to this point R, okay? And that's how I'm going to calculate the potential from the electric field, okay? So this is my start point, this is my end point, this is my electric field, that's my path or my line integral. I know in this particular case, I'm going to say I know what that electric field equation is. Okay, I could have found it with Gauss's law. Something like this. It's going to be Q over R squared dr. Okay, and then when I do that integral, I'm going to get 1 over 4 pi epsilon naught Q over R. Okay, I'm going to look at it for a second and make sure that if I took the derivative of that, I would still get, right, what I just did the integral of. That's how I always check and make sure I did the integral right. I got to evaluate that at my boundary points. Okay, when I do that, I'm going to get 1 over 4 pi epsilon naught Q over R squared minus the second bit, which hopefully you guys see is going to be 0. The second bit's going to be 0. So I'm just left with that first term. All right, if I want to now go a little bit further, and now I want to figure out what the potential looks like inside my sphere. Okay, now if I'm going inside the sphere, actually, I have to still go all the way from infinity all the way in. So I got to continue this bit. I'm going to draw another little bit here. I'm going to take it all the way from infinity. This is going to start at infinity and I'm going to integrate it all the way to R. And then I got to go again from R all the way to little r. Okay, this means I have to do 2 sets of line integrals because the electric field is different here than it is here. Okay, so I've got E out here, which is different from my electric field in. All right, so I got to do it in 2 bits here. So I'm going to start with the outer one. That's going to take me from infinity to the outer radius of my sphere. Okay, and that gives me E out dot dl. Oh, I screwed this up. I'm kind of going between R and L. This could, oh, I'm going to leave this as L. Okay. This is going to go dr. And by the way, I'm doing R because this line integral, I'm taking it along the radial direction. So I'm just integrating in the direction R. I hope that makes sense. Okay. I'm going to add to that the second part of my integral where I'm going from R to little r, which is a point inside my circle. But now I've got the electric field inside that shell that I have to evaluate over. Okay. So this second integral is really easy to do because the electric field inside a spherical shell like this, if it doesn't have any other charges inside of it, is 0. Okay, so that makes it a lot easier than some problems I could give you. So Vn ends up being 1 over 4 pi epsilon naught. Okay, Q over R. I'm going to evaluate this from R to infinity. And that gives me 1 over, sorry, got a sign error here, get rid of that. That gives me 1 over 4 pi epsilon naught Q over R. Okay, this is good. Okay, so this is the first part. It's continuous here because if I compare, I'm going to compare this term here to this term here. Okay, potential has the same value. Okay, as you approach R equals R from either side. All right, let's use the second bit. So that basically gets at the fact that this potential, it's always continuous, okay? It's continuous at that boundary, even for this sphere. Hopefully you guys could actually draw this potential, by the way. God, made a lot of errors in this. Sorry, this should just be an R. Hopefully, eek. That should also, sorry guys. I could re-record this, but I think I'm just going to leave it. I don't know why I put a square there. There's no square here. So that should just be an R, and there's no square here either. Okay, so go back and fix that in your notes. Sorry, I made a mistake. All right, so let's use this second relationship. I know that the if I take the rate of change in the direction normal to the surface above, and I subtract the rate of change of the potential normal to the surface below, I should get this relationship that it is equal to negative of the surface charge density over epsilon naught. So let's see if that is true in this case. So I'm going to take, this is what I want to find. I'm going to take the gradient of the potential on the outside of my shell. Okay, that's going to be equal to the gradient of 1 over 4 pi epsilon naught Q over R. And I want to evaluate that gradient at that particular surface point. So I'm going to evaluate it at R. And when I take that particular gradient, this is going to be like a partial derivative with respect to R. I, not surprisingly, get something back that looks like the electric field, except I'm going to plug in the big R for the little r, so I get that value. And I'm going to do the same thing. Now I'm going to do it from the inside. Evaluate that at R. Okay, in this case, it's just equal to 0 because this is the partial derivative with respect to little r, and this is a big R. Okay, so that's a constant. So we don't have any R dependence on the voltage inside our shell. Okay, so we end up getting that V out minus our delta V in. So we end up getting that our partial derivative of V out minus that partial derivative of V in is equal to just this negative Q over 4 pi R squared. I'm going to put that in parentheses, times 1 over epsilon naught. Hopefully you guys can see that this is equal to the charge divided by the volume of a sphere. Okay, or sorry, this is the charge divided by the area of a sphere. Okay, so this indeed looks like the surface charge, negative of the surface charge, divided by epsilon naught. Okay, I'm going to end it there. Sorry, I made a few typos in that one.